Hello students, in this demo lecture, let's quickly cover the concept of potential energy in the framework of a calculus-based undergraduate course or high school course. Now, especially if it is AP Physics, C Mechanics or IIT JEE or NEET, CBSE, ICSE, all these syllabi deal with the concept of potential energy that we will be discussing in this particular lecture. Now, if you think you understand potential energy very well, then I have a very simple question to ask. Try to answer this. Now, if I talk about kinetic energy, if I talk about kinetic energy, the formula is K, that is half m v squared, right? You know this formula very well. Single formula, a mass moving with a speed v has the energy of actual motion. So what is this? Kinetic energy is the energy of actual motion, right? But when it comes to potential energy, the formula, I mean, it's not the same. There is no unique formula for this, right? For example, if I talk in the context of gravitation, then the potential energy becomes negative G m1 m2 over r. Now, if I talk in the context of electrostatics, then U becomes K Coulomb's constant times Q1, Q2 over R, right? And that's not it. If I go to talk about spring potential energy, then what happens is the spring potential energy is going to be U, that is half K x y, where K is the spring constant. Now, again, if I talk about simplified gravitation, a simplified gravity, then I will talk about the potential energy is U equals to mgh, which is the formula that you've been using ever since you entered high school physics, right? U equals to mgh. Now, why do we have so many formulas for potential energy? Why not? Why is potential energy not as simple as kinetic energy? What is your answer? Let me know in the comments. Right. Anyways, so the secret, I mean, the answer actually lies in the word potential. Right? When we say potential, it's actually stored. Potential simply means stored. But stored where? Stored in a system. Like depending on the nature of the system, you have different formulas. Yes? Right. Like I'll basically explain this to you with a very simple example. Now let's just first note potential energy is the energy of stored motion. Right? It's the energy of stored motion. Yes. Now you see, imagine, let's talk about actual food. Let's take apple for an example. An apple is actually food. It's actual food. Um, you can have the apple as your food in India, in the US, in UK, in Australia, everywhere you go, an apple remains an apple that can be eaten as food. But imagine if you have a lot of apples and you don't want them to rot. So basically, you want to store it for future use, right? So in this case, you might have be needing a refrigerator to store it for a for the future time, or you might not be actually buying so many apples. Instead, you will be storing some money so that you can exchange that money in the future for actual apples. So when it comes to storing the apple in the form of money, you would need a bank account. You would be needing currencies. Now, if you are in India, you will be using Indian rupees. If you are in the US, you will be using US dollars, in Australia, Australian dollars, in UK, pound sterling, and so forth. So, depending on the system that stores energy, you will be using a formula, right? So that's exactly why potential energy has different formulas. Now, let's dive deeper into the concept. Now, if we have a system, right? Now, since we have just discussed about a system, imagine if I have a system here, right? And let's suppose I have again, this system needs to expand by an amount x. Let's suppose whatever is the potential energy in this state. Let's call it the potential energy is ui, right? Whatever that is. Now you would be expanding the system a little bit. Let's say you are expanding the system by an amount x. So in this case, the potential energy is UF. So how much is the potential energy stored? Change in potential energy is U final minus U initial. Understand? That's what makes sense. Whatever you can assign UI any value. The only thing that makes sense is delta U, change in potential energy. So whatever is the initial potential energy, final potential energy will be just the initial plus the change. Clear? Now, would the system on its own, you know, generate potential energy? No. There has to be an external force, right? There has to be an external force that actually does some work, and that is WEXT, right? And that external work gets stored in the system, but not so fast. Not all of the external work done by the external force or W external gets into the system and gets stored. No, I'll tell you. And again, before I get to that, what is the work done by the external force? I know you might be tempted to write it's the force, external force multiplied by the displacement. No, you're not in elementary high school anymore. You are doing a calculus based course. So understand this formula is applicable only for constant forces, right? You won't be using this formula if the force varies, and an external force might vary. So what will you do if the force varies? So in this case, we are going to use calculus. So let's say that I have a graph in which I plot the force and the displacement, right? Now, if the force varies like this, now how would I know how much is the work done by the force in going from, let's suppose this is x1 to x2? If the displacement starts at x1 when the force was F1 and the displacement ends at x2 where the force is F2. How would you know? The force varies. You can't use this formula anymore. So before I get to that, once again, what's the formal definition for the work? The work by a constant force. Now that's not just F into displacement, Fx. No. The thing is, imagine if the force is this and the displacement x is at an angle theta. So in this case, what you need is the work done by the force is the force that is along the displacement, is the component of the force that is along the displacement that is actually responsible for the displacement. The other component, right, which is F perpendicular component, which basically has nothing to do with the displacement, will not be doing any work. So the work done by a constant force W is what? It's force dot x. Yes or no? Why? It's because the fx component is just f cos theta, right? Trigonometry, the component of the force along the direction with which it makes an angle theta would be f cos theta. Now with this, we can just write work done is equal to force f cos theta into x, which I can just write it as fx cos theta. And you know the dot product of two vectors a dot b is av cos theta, right? Imagine if there is a vector a and there is a vector b and the angle between them is theta, then the dot product, which essentially means the combined scaling effect of the vectors, right? That's AV cos theta. So I can use the same thing here. I can just turn this back into this formula. So work done by a constant force for a displacement x would be F dot x. And if they are in the same direction, then theta is 0, so cos theta is 1. They are in opposite direction, theta is 180, and F dot x would be negative Fx, right? Anyways, so if we come to this, now imagine the force varies, yes. So it becomes very difficult for us to um, use this formula, right? We can't use this formula here. But the technique here is to use calculus. Imagine for any x, I have already a force value, right? But the force will change only if I consider a section of displacement that is too large. What if I consider a section of displacement which is infinitesimally small? That means I consider a section of the displacement which is very, very small. That means it's essentially the same force that is responsible for this dx, right? I will say dx, the small section of displacement. So dx is the elemental or infinitely small displacement. Yeah. Now in this case, force remains constant, so I can use the work done, but is it actually work done? No. It's elemental work done dw, that is F dot dx. Clear? So for this, I know the work dw is there. But what about the entirety? For the entire section, well, if I could add all these small strips, infinitely small strips together, in other words, that would be the area under the fx graph that will help me find the total work done. So, area under the graph is what? Integration. So, the work done will be integration of f dot dx from x1 to x2. Yes. Now in this case, the work done by the external force would simply be integration from x1 to x2 f external dot dx. Clear? But is all of the work done by the external force getting stored in the system? I'll give you a very simple example where you can see if all the work will be done by the external agent will be stored in the system or not. Imagine you are doing camping. Now there is a stream that where clean water flows. So when you're doing camping, you would be having a few bottles to store water for the night, right? Now, if you go to store some water for the night, how much water you end up storing, does it depend on how much water flows in the stream, or it depends on the capacity of your bottles? Your storing capacity. It depends on your storing capacity, right? That means the energy that will be stored in the system from the work that the external agent does depends actually on the internal force, not the external force, right? So if I take you back to this example here, right? Let's say, understand here in this case, it will be the internal force, and of course, the internal force will oppose the external force, right? Newton's third law of motion, right? But then this internal force has a limit, right? It can go up to a certain extent. The external force might not be limited to the system. The external force does not depend on the system. This particular system might have a limit on the internal force that it will apply on the external agent, action reaction, right? However, there are two things that we need to understand here. First thing is the internal force could be of two types, right? Sorry. The internal forces of a system could be a dissipative force like friction. A dissipative force is known as non-conservative force. And Apart from dissipative, you could have a force that actually stores. For example, a spring stores energy. Friction does not store energy. Air resistance does not store energy. Gravity stores energy. Electrostatic repulsion or attraction stores energy. So you have a force that conserves energy, that is called conservative. Storing is also known as conservation, right? So conservative force. So the work potential energy is only applicable to conservative forces, not for dissipative forces. Now, let's go back. So here, the internal force that will be responsible for storing energy is the internal conservative force, FINTC. Right? This is the internal conservative potential energy. Sorry, internal conservative force. Now, if now understand the since the internal conservative force is a property, it depends on the property of the system. It might have a limit. It cannot go beyond the limit. However, the external force does not depend on the system, right? So there would be a component of the external force, right? The component of the external force that would be balancing the internal conservative force, right? Which is negative. Yes, imagine if I call my internal conservative force as FINTC, then the part of the external force will be negative of that internal conservative force, right? It's called negative FINTC, right? They're opposite in nature. That's why I included a negative sign. Including a negative sign doesn't mean the external force is negative. It's just that it's negative of the internal conservative force. So the external conservative force, understand here, if I write clearly, understand. Imagine if the external conservative force has two parts. One is the negative of the one is the part which basically balances the internal conservative force. This balances FINTC. That's exactly why the external agent is able to somehow drive the system outward or drag or expand the system, right? Plus F external dash, that is the extra force, right? For example, imagine when you are raising a ball, right? I'll give you a very clear, simple example, right? Understand here. Imagine if you have a ground and there is a ball of mass 5 kg. And let's suppose G's value, gravity's value is just 10 meters per second squared. Just take it for example. Now understand, this ball is not actually alone. There is earth here, right? Basically, it's a system. You might think that the ball is the only body. No, it's entirely a system. The entire thing is a system. Now, when an external force, let's suppose, imagine if I apply an external force of 5 newtons, will I be able to raise the body? Will I be able to do any work at all? No, because there is a downward mg force acting on this, that is 50 newton in magnitude. Weight, right? The weight force is mg, right? This is your mg force, 50 newton. So I can't raise this ball by applying a 5 newton force. How much minimum force should I be applying? Minimum is 50 newton upwards, right? Imagine if I end up applying a force of 60 newtons. So out of the 60 newton, 50 newton will encounter the downward 50 newton, and the extra 10 newton is the extra force. This extra force would basically be not contributing to the potential energy of the system. It's the only the force, the force, the part of the external force that is equal and opposite to the internal force, conservative force, that will only end up doing work which will be stored in the as the potential energy of the system. So what happens to the work done by the extra force? It just appears as this is responsible for increase. So it increases the kinetic energy, right? It increases the kinetic energy. The extra force increases kinetic energy, but we are not talking about kinetic energy right now. We're talking about potential energy. So we will be only taking in the diagram, we will be only dealing with this component of the external force, which is negative negative FINTC, negative of the internal conservative force. That component of the external force will be responsible for doing work that will be stored as potential energy, right? So now let's sum it up together. So now the change in potential energy, which is the final potential energy minus the initial potential energy, that is equal to the work done by the component of the external force that cancels the internal conservative force, right? So if it is negative FINTC dot dx going from x1 to x2. Now, can I not just make a slight change and bring the negative sign outwards? So in essence, it's negative of what? What is this? What is x1 to x2 f internal conservative dot dx? This is nothing but work done by the internal conservative force. So this entire thing, right? This entire thing is this. So I can just write the change in potential energy will be negative of the work done by the internal conservative force, right? So let me write it neat and clean. So the change in potential energy in every system is basically the final potential energy minus the initial potential energy, which is negative of the work done by the internal conservative force, which in essence is equal to negative of integration of F internal conservative dot dx from x1 or x initial to final. So let's just write it as now initial to the final x. Okay. So I think I hope that you've understood this uh, this derivation, right, and the concept that we discussed. Now, if you have any doubts, then you can just reach out to me on the link that is thephysicist.in/ask. It's probably uh, you know crawling at the bottom of the video, right? So see you in the next class, right? All the best for your studies. Bye bye.